Okay, so page 13, we're going to use the formula that we just derived, which is the volume is equal to pi times the integral from a to b, which are your bounds, of f of x squared dx. Now remember, when you're dealing with the revolution being and the slice being perpendicular to the x-axis, this is still technically top minus bottom. So if you want to think of f of x being equal to the top minus the bottom, that is okay. But right now what we're doing is revolving around the x-axis, so the bottom is actually going to be where y is equal to 0. So what we want to do is find the volume of the solid formed by revolving the region bounded by this graph and the x-axis, which is where y is equal to 0, from 0 to pi about the x-axis. Okay, so first of all, what we have is this region, so we need to take a look. It's going to be the square root of the sine of x. So if we were to go from 0 to pi, okay, the sine of 0 is 0, the square root of 0 is 0. The sine of pi is 0, so it goes here. So let's deal with the sine of pi over 2, dead smack in the middle. Sine of pi over 2 is 1, the square root of 1 is 1. So we're looking at something like this. So the issue here is you would have to get all these points in between, but if you know what the sine curve looks like, it's going to look very similar. So it would look like this. Oops. Okay. So this is actually, if we were to revolve this all the way around, you would think about this coming around this way to create this full shape. And then what you have is this radius right here, because this would be revolved all the way around like this. So there's your disk. There's your circular shape. So this is going to be my radius. And the radius would actually consist of my top function, which is the square root of the sine of x, minus the bottom here, which is 0. So then your radius is going to be the square root of the sine of x. So then in this case, they give us our a and our b, which is from 0 to pi, so they give it to us straightforward. And again, here it says that this is perpendicular to x, so this would be y equals something dx. Okay, so I'm just trying to stay consistent. Okay, so what we have, again, is if you're dealing with the area of this circle, okay, the area of the circle is going to be pi r squared, and your r is going to be your top minus your bottom, and when you square this, it's the sine of x. So if you're looking for your radius, when we plug this in, it's top minus bottom, so the volume here is going to be equal to pi times the integral from 0 to pi of our top minus our bottom, which is just the square root of the sine of x, squared dx. So in this case, we should be able to do this without a calculator. The square root of sine of x squared is just the sine of x, so this is equal to the pi times the integral from 0 to pi of the sine of x dx. So when we integrate this, we end up with negative cosine. So this is negative pi times the cosine of x to be evaluated from 0 to pi. So we'll leave the negative pi on the outside. Cosine of pi minus the cosine of 0. Cosine of pi is negative 1 minus 1. So this is negative pi times negative 1 minus 1. So this should be 2 pi. Okay. So, volume by washers perpendicular to the x-axis. So a washer is just like a penny with a hole in the middle. And in this case, it says not all solids of revolution have solid interiors. Some will have holes or some kind of channel. So remember I said that you wouldn't necessarily have a situation where your solid is going to be totally parallel. You could have something where maybe there would be a line here and this would be all filled in and this channel would be open here. So it's just going to create a very small hole, but it's still considered a washer. So here, if f and g are continuous and non-negative functions on this closed interval from a to b, what we want to suppose is that f of x is greater than g of x. So this should look familiar to you in the sense that f is above g. And it doesn't matter what they're labeled, they're just picking arbitrary f and g, whichever one is above the other, and it's still on this interval from a to b. So what they're saying is that R is this region that is bounded above by f of x and below by g of x, and on the sides, meaning that you have a boundary to kind of close this region off by the vertical lines of x is equal to a and x is equal to b. So the volume of this solid that is revolved around this region, around the x-axis, is going to create a hole. So we can actually solve this problem, again, by slicing, and we're going to say that this cross-section is taken perpendicular to the x-axis at some given point x. So what's going to happen is we're going to create some hole in this region. So we have a washer-shaped region with the inner radius of g of x and the outer radius of f of x. So before I go through this whole thing, I want to take a look here. So what they're saying is that we have our region of f of x, which is on the top, like this, and g of x, which is on the bottom, okay, but not adjacent to our axis of revolution. So this right here is my axis of revolution, the x-axis. And what happens is when we close this off from A to B, and we take this region and we revolve it around the x-axis, we get this channel or this hole in the middle, which is what you see below in that figure right here. Okay? So this is what they're talking about. So what we have to take a look at is if we go from the very top, which is going to be our region R, or let's call it our capital R, and then to the very bottom, what that creates is a hole here.